Hello students, and welcome to our video covering topics in section 3.3 of your textbook. In this video, we will cover the dimension and Rank-Nullity Theorem. So, all right, starting with dimension. To have a fruitful discussion of this, we're going to need to return to the concept of a basis. So, recall that the vectors v1 to vm in some subspace V of Rn will form a basis of V if two things happen. One, they span V, and two, they are linearly independent. So that's what we need. We need to have a basis. It has to span your space, and the vectors have to be linearly independent. Now let's also recall that a space can have many different bases. So even just thinking of R2, we've got our standard basis, which are the vectors 1, 0, and 0, 1. But we could have any number of alternate bases. Really, so long as you have two vectors that are independent from each other, they're not pointing in the same direction, then you can use these to get any other point in R2 by taking linear combinations. So, okay, a basis, or the basis of a space isn't unique. However, here's an important fact about bases. The number of vectors in a basis, it's the same no matter what your basis is. So all bases of some subspace have to have the same number of vectors. So like in R2 we just looked at, all bases of R2 are going to have two dimensions. And this might seem, maybe you have kind of accepted this already without knowing that this is actually a theorem and something that needs to be proved. And so we are going to prove it because it's important, and it's important for a number of reasons, but one of which is that it allows us to define the dimension of a subspace, because now we'll define dimension as the number of vectors in the basis. So, and that can only be done if the number of vectors in the basis is only one thing, and it doesn't depend on what basis you choose. So, okay, let's prove this theorem that the number of vectors in a basis is the same no matter what the basis is, so long as you're looking at the same space. Okay, so here's our proof. Our strategy is going to start assuming that we have two distinct bases, and then we'll show that these two bases just have to have the same number of vectors. I hesitate to say this, but I will note that your book talks about this proof in kind of a disparaging way and says, this proof is a little technical and not very enlightening. And I'm doing it anyway, so I feel like I have to explain why. And the reason is because even though I guess a lot of the steps are unmotivated or just motivated by the fact that it works, it uses a ton of ideas that we've already seen in this class. And so I think it's a great way to illustrate lots of concepts we've already seen, seeing them come together to prove an important theorem. So, okay, let's jump in. Let's start by supposing, all right, we've got two bases, this basis V1 to VP and W1 to WQ. And right now we're agnostic about whether P equals Q or not. So these are each a basis of V. And now our first step is to say, well, since, say, W1 to WQ is a basis, that means any of these vectors in V has to be a linear combination of these vectors W. That's just, that's because each of these VI is in the span of these. This is what it means for the W's to be a basis. So, okay, let's write it out. So I'm saying V1 is some linear combination with coefficients C11, C12, all the way up to C1Q. Some coefficients on the W's. All the way down to VP has some coefficients, also some linear combination with some coefficients CP1, CP2, all the way to CPQ on the vectors W. At which point you should be like, okay, that's nice. What are we going to do with this? Well, the key to this proof is, or one key, is to recognize that this information can be rewritten in terms of matrix multiplication. So let's take a minute to convince ourselves that all of this information here in these equations, that this information is captured exactly by this matrix vector multiplication. Okay, so let's see. If we're doing matrix vector multiplication here, we take the first column. First let's say what are these matrices? So this matrix is the columns of the basis W1 to WQ. This matrix is the matrix of the coefficients, and they are written kind of like flipped. So the coefficients on this first row here that's the coefficients. Those are lined up in this column. And the last row of coefficients gets lined up as a column in this matrix. And then the last matrix is the matrix where the column vectors are all V. The V basis vectors. Okay. All right. So yeah, let's convince ourselves that this really is containing the same information. So, all right, take the column C1 to CQ, multiply it by this matrix. Well, in the column version of matrix multiplication, that's just the linear combination of W1 to WQ with these coefficients, which we have said is V1. Similarly, if we had looked at the column of coefficients on V2, well, all right, multiply that column by the matrix. You get the linear combination that ends up being V2, all the way to the last column of coefficients multiplied by the matrix of W columns gets you a linear combination that ends up being VP. So it really is the same information. Now, before we move on, let's make sure we know the dimension of these matrices. So let's say this first one. Well, we know it has Q columns, and how many rows does it have? Well, it's a subspace of Rn, and so these got to be n-dimensional vectors. So this is a n by q matrix, and I'll follow your book and call it matrix B. This matrix here, this is looks like a p by q matrix, and again, following your book, we'll call it matrix C. And then our final matrix, this is going to be an n by p matrix. We'll call it matrix A. All right. Woo! Right? What have we done? What did we get here? Well, here's our next unmotivated step. Let's note that since V1 to VP, they're a basis, which means they're linearly independent. And if they're linearly independent, then the kernel that you get, the kernel of the matrix of these vectors is the columns. That kernel is going to equal 0. This pretty much follows from the concept of linear independence. So the kernel of this matrix is 0. But notice that this matrix is just equal to B times C. So that means the kernel of B times C equals 0. But this actually implies that the kernel of C by itself equals 0. Now, this follows from a question I asked on your pre-assignment. You showed that the kernel of C has to be a subset of the kernel of B times C. And so, since the kernel of B times C is the 0 vector, and kernel of C is a subset of the 0 vector, that just means kernel of C has to be the 0 vector itself. So, the kernel of Z is the 0 vector. What does that get us? Well, that tells us that the columns are linearly independent. This is like an if and only if statement up here. So, kernel of C is 0. The columns are linearly independent. And that tells us that the rank of C is P. So the rank of C has to equal the number of columns. Since the number of columns are all linearly independent, you take the reduced row echelon form. These are all going to be leading ones. You're going to get a leading one in every column. So the rank is equal to the number of columns. But now, the rank of any matrix it can't be bigger than the number of columns, and it can't be bigger than the number of rows. And in fact, it's going to be less than or equal to the minimum of your columns and rows. And so since P is equal to the rank of C, this means P has to be less than the minimum of P and Q. That means that P has to be less than or equal to Q. Okay, so all that work to get that P is less than or equal to Q. But notice, if we just switched the roles of V and W in this whole argument, we would have ended up at the point saying that Q also has to be less than or equal to P. But if P is less than or equal to Q, and Q is less than or equal to P, then Q and P have to be equal. So there we go. They had the same number of vectors. Okay, maybe you agree with the author, technical and unenlightening, but notice the concepts it brings together. Basis, linear combinations, column version of matrix multiplication, dimension of matrices, linear independence, its relationship to the kernel, subsets of kernels and relationship between kernel and matrix multiplication, rank, the relationship between the rank and the rows and columns. There's a lot going on there that we've seen before, and now it's all coming together. I really hope that was worth it. So if you're still with me, all right, let's see where this is going. The whole point of this is so now we can define what the dimension of a space is, or a subspace. So if we have some subspace V of Rn, the number of vectors in the basis of V, that is the dimension. And okay, just a little terminology, dim V means the dimension of V, which means the number of vectors in a basis for V. And now I'm not going to prove all of these little facts about bases or about dimension, but these are nice to kind of have in mind, and I think you could maybe justify them to yourselves pretty quickly based on our earlier discussion. But yeah, this is something you should have in mind is that, all right, if you're looking at the dimension of some subspace and that dimension is M, well, if it's in M dimensions, that means that there are at most M linearly independent vectors in that space, in the subspace. And you need at least M vectors to span that space. I think probably the most interesting one of these is C. If you have M vectors that are linearly independent, then they do form a basis. And so this is nice. You might use this. Say if you're asked, find a basis of this subspace. And you might go about by finding some linearly independent vectors, and you can know that if you find M of them, you've found enough and you don't have to look anymore. You've got your basis. And then another thing is that if you have M vectors in your space and they span the space, then all right, you've got your basis. Okay, so that's our dimension discussion. Let's move on to the Rank-Nullity Theorem, something we can prove now that, or even just understand what it is now that we've got the concept of dimension solidly under our belts. So, okay, we're going to start this discussion by considering the dimensions of the kernel and the image of a matrix. So in our first example, we've got some matrix here. Looks like a 4x5 matrix. And our first task is to find a basis of the kernel of A. And then once we've got a basis, we'll count the number of vectors in it, and that'll tell us the dimension of the kernel. So, all right, let's go about doing that. In order to find the kernel, as you know, we have to solve the system AX equals 0. In order to do that, we find the reduced row echelon, set up that system, find the reduced row echelon form of that system, and then I trust you've done this enough times, you translate this back into equations, and then you solve for your leading variables, and you separate, you make your free variables parameters, you separate out, and you get something like this, where your x vector is equal to, we've got 3 parameters because we have 3 free variables. And so this is our kernel. It's the span of these 3 variables, or these 3 vectors. Okay. But now we ask, are these vectors, we'll call them W1, W2, and W3, do they form a basis for the kernel? Like, does this mean the kernel is three-dimensional? Well, I claim they definitely span the kernel. And that's because we have this equation. X is S times W1 plus T times W2 plus R times W3. And X is just any vector in the kernel. And so any vector in the kernel can be represented as a linear combination of those vectors. So yeah, those vectors span the kernel. But are they a basis? Are they all linearly independent? I claim, yeah, they're linearly independent by using the zeros test. At which point you're like, zeros test? We definitely have not talked about that before in this class. And your book mentions it back in the previous section. And let me just quickly state what the zeros test is. The zeros test is basically the idea is if you have any number of vectors, and in one of the and in one of the components of or say one of the rows, you have one or something non-zero component in one vector, and then the corresponding components are zero in the other vectors, then this vector with the non-zero component here can't be a linear combination of the other two. The idea is just you can't multiply zero by, it doesn't matter what S and T are, multiplying them by zero, you're not going to multiply and add together and get something that's not zero. And so the zeros test is if you've got a component, you've got a non-zero number in one and zeros in the other vectors, then you've got linear, then this vector is independent from these two. And we actually can do the zeros test on all of these. This has say the second vector has a 1 in the second to last component. The other vectors have zeros there. So this is independent from these two. And similarly, this first one has a 1 in the second component. These have zeros in the second components. So by the zeros test, these are all independent of each other. And so, in fact, they are linearly independent, they span, they are a basis. And so let me draw just a couple general conclusions here. First off, whenever you solve for the kernel like this, the number of vectors you get is always going to be the basis. The vectors you get are going to be a basis. So you always know that the dimension of your kernel is going to equal the number of free variables. And the reason you can kind of know this is that, free variables, remember you turn them into parameters. And then when you are separating everything out, when you put back into equations and then you separate out to get this vector form, you have, all right, since our second variable was a parameter, you have x2 is just 1 times the parameter you gave it, s, and 0 times the other ones. So you're going to get the zeros test telling you that this first vector is going to be independent from all the other ones. And then similarly, you've got t was substituted in for x4, because x4 was a free variable. So you're going to have x4 is going to be 1t and 0 else. Similarly, x5 is going to be 1r and 0 of the other vectors. And so you're going to, when you find the kernel this way, you're always going to have the zeros test tell you that they are independent, and you already know they span the kernel. So yes, the number of vectors in the kernel is equal to the number of free variables in the reduced row echelon form. Okay. Now let's talk about the image. How do we find a basis of the image of A? And then, all right, once we've got a basis of the image, let's talk about the dimension of the image. Well, we know that the image is the span of the column vectors of A. So finding vectors that span is easy. All the column vectors together, that set spans the image. And we just need to get rid of the redundant columns in A. And the way to do that is, this one weird trick your math professors don't want you to know. It turns out that the redundant vectors in your matrix A correspond to the free variables in the reduced row echelon form of A. So let's see this in action, and then we'll talk about why it works. But yeah, so once you know, so the free variables in the reduced row echelon form, those will correspond to redundant vectors in A. And so then the basis for your image are going to be the vectors in A that are corresponding to the leading variables in the reduced row echelon form. So if we're trying to use this idea to find the basis of the image of A, we find the reduced row echelon form of A. The leading variables correspond to the first and third columns. And so this means that the first and third column vectors of A are going to be the basis of the image. So in one sense, this is an easy test to perform. It's kind of easier than finding the kernel, especially if you're having a computer compute reduced row echelon form for you. But why do we know that this works? In particular, why do we have this relationship between A and the reduced row echelon form of A, where the redundant vectors in A are just the free variables in the reduced row echelon form? Well, if we look just at the reduced row echelon form, it's pretty straightforward actually to see how to build free vectors out of the leading vectors, and so to show that these free vectors are redundant. So let's name all of our vectors here. So in A, we'll have our column vectors be A1 to A5, and in the ref A, it'll be B1 to B5. And looking at reduced row echelon form, we can see right away that this second vector here is just 2 times the first vector. It's only non-zero in one component, and so multiply that the first column vector by 2. There you go. So, all right, column vector 2, redundant. We don't need it because we've already got 1, this first column vector. And if we wanted anything built out of column vector 2, well, we can build it by multiplying first by the column vector of 1 by 2. Similarly, all right, B4, we can see that this vector is going to be equal to 3 times the first column vector times plus -4 times the third column vector. So we get that relationship there. Again, B4 is redundant. Similarly, B5, that's going to be -4 times the first vector and plus 5 times the third vector. So again, B5 is redundant. We didn't need it. Turns out, looking at this, we only need B1 and B3 to make the rest of these vectors. So since B2, B4, and B5 are redundant in the image, and B1 and B3 are linearly independent, do the zeros test, then B1 and B3 are going to be a basis for the image of the reduced row echelon form. Now, you might be celebrating, but hold your horses. In general, the image of your original matrix A is not the same as the image of the reduced row echelon form. But let's look again at this first relationship. The B2 is equal to 2B1. Well, let's rewrite that as 2B1 minus B2 equals 0. And the reason I want to do that is because looking at it this way, this tells us that, this relationship lets us know that 2, the vector 2, -1, 0, 0, 0, this is going to be in the kernel of the reduced row echelon form. And just check, do it, multiply it through. You'll see this is in the kernel of the reduced row echelon form of A. And the key is that it is also in the kernel of A. And the reason we know this is that this is the whole point of finding reduced row echelon forms of a matrix, is that the process doesn't change what your solutions are. This relationship tells you that this is in the kernel of reduced row echelon form of A and in the kernel of A. But if this is in the kernel of A, then all right, multiply this by the matrix A. And your column version of matrix multiplication tells you that, that means that 2 times vector A1 minus vector A2 equals 0, which in turn tells you that vector A2 is just 2 times vector A1, which is the exact same relationship we had amongst the vectors in B. And so indeed, the same relationship that holds of the vectors in the reduced row echelon form, that relationship will also hold for the vectors of A. So even though their images are different, the relationship between the vectors is going to be the same. Maybe just one more example. We had the second relationship, B4 is 3B1 minus 4B3. All right, make it a linear relation, set it equal to 0, and then, or solve it so that it's equal to 0. This tells you that 3, 0, negative 4, negative 1, 0 is in the kernel of both ref A and kernel of A. Then that means multiplying this by our matrix A, we get the relation 3A1 minus 4A3 minus A4 is 0. And solving for A4, we see that, okay, A4 must be redundant in the matrix A because we can build it out of A1 and A3. And your book actually goes through this one in detail to show that B5 minus 4B1 plus 5B3 really implies that A5 is minus 4A1 plus 5A3. So, okay, we have that the free variables are all in the span of the leading variables, and so they're redundant. And the leading variables are not in the span of each other because of the zeros test, and so they're linearly independent. And there we go. That's what we wanted. That means that if we just take the vectors that correspond to the leading variables in the reduced row echelon form, those will span the image and be linearly independent. They'll be a basis. And now note that this means that the number of vectors in the image is equal to the number of leading variables, which is the rank of our matrix. So let's, why did we just do all that? So let's summarize what we know from this example. We know the dimension of the kernel is equal to the number of free variables in the reduced row echelon form. We know the dimension of the image is equal to the number of leading variables in the reduced row echelon form. And since all variables are either free or leading, this gives us what's known as the Rank-Nullity Theorem. And so this theorem says if you have some n by m matrix, so the number of columns, read variables in the matrix, is m, then we have this equation that the dimension of the kernel plus the dimension of the image is equal to m. This thing, basically the number of free variables plus the number of leading variables is the number of total variables. So, all right, a little bit terminology. All right, the dimension of the kernel is called the nullity of A, which I guess makes sense when lots of books call the kernel the null space, and so the nullity is just the number of dimensions of the number of vectors in the basis of the null space. And then we already saw that the dimension of the image that's just going to be the rank. And so sometimes this equation here, which is what we will really talk about in class and use a lot, it can be rewritten as the nullity of A plus the rank of A equals M. And that's why it's called the Rank-Nullity Theorem. And your author notes that some books go so far as to call this the fundamental theorem of linear algebra. And in one sense, you might think, why? I mean, in one sense, if you're just thinking about it as, well, of course, the number of free variables plus the number of leading variables equals the number of total variables. But really what this is doing is it's relating the dimension of the image, the dimension of the kernel, which is a subspace of the domain, with the dimension of the image, which is a subspace of the codomain. And so that right there is maybe a little surprising because these two spaces live in totally different spaces. But really, I think it's sometimes called the fundamental theorem, because in some sense, the Rank-Nullity Theorem really does characterize how we think of linear transformations. If you're telling, I guess, if you're interested in a linear transformation, what do you care about? Like mathematicians really think, well, all right, what does it send to 0, and what is in the image? And here we have, this deep relationship between the two. And so you could do something like say, oh, you're in 3 space, and maybe your linear transformation is projection down onto the xy plane. Well, the xy plane has dimension 2, and so you know right away that an infinite number of vectors get sent to 0 because you have a whole one-dimensional subspace get sent to 0, because you know the dimension of the kernel is equal to the total number of dimensions minus the dimension of the image. Okay. Man, I think that was enough heavy lifting for one video. I'll see you in the next one.